Hi and welcome to the lesson of partial differential equations. So in today's class, we are going to solve inhomogeneous heat equation using the method of Adomian decomposition. Now we are given the equation ut equals uxx plus sine of x. As we can see that there is a source term, therefore it's an inhomogeneous problem. Now we can approach this problem in two ways. Either we can use the t direction or we can use the x direction. So let us solve in the t direction first, where LT inverse applied on the function is the integral of the function from 0 to t, and Lx inverse applied on the function will give us the iterated integral of the function with respect to x. Now if we apply uh, LT inverse on both sides, so we get this expression plus LT inverse of sine x. Now on simplifying, on the left hand side we have u of x comma t minus u of x comma 0, and on the right hand side we have this term and plus the LT inverse of sine x gives us t sine x, because we are integrating this with respect to t from 0 to t. And further, if we simplify this term goes to the right side, which is given as cosine of x. So this is cosine x plus t sine x plus LT inverse uxx. Now u naught is equals to this function, that is cosine x plus t sine x. Then u1 is the integral from 0 to t of the function, but we have to differentiate it twice because inside we have uxx. So if you differentiate this, we'll get negative cosine x minus t sine x. And now we can integrate this, so we get negative t cos x minus t squared over 2 factorial sine x. Similarly for u2, now we have to differentiate this function again twice, so we get t cosine x plus t squared over 2 factorial sine x. And now if we integrate this, we are going to get t squared over 2 factorial cosine x plus t cube over 3 factorial sine x. Now in the similar way, we can find u3, u4 and up to un. Therefore, we will get a series. We can just write it here. We will get a series expansion. So we know that the function u of x comma t equals u naught plus u1 plus u2 plus so on. Therefore now u of x comma t equals cosine x plus t sine x, and then u1, that is minus t cosine x minus t squared over 2 factorial sine x, then plus u2, that is t squared over 2 factorial cosine x plus t cube over 3 factorial sine x, and so on. Now if we simplify, we take this cosine of x as a common, so we are left with 1 minus t plus t squared over 2 factorial dot dot dot, and sine x as common here, so we are going to get t minus t squared over 2 factorial, and so on. Now this expression here is nothing but the Taylor series expansion of e to the power negative t centered at 0. Therefore, we can write it as cosine of x times e to the power negative t plus sine of x times. Now here we can see that we have this expression, but if we add -1 to this expression, we can get a series expansion. So if we want to add 1, we have to subtract 1 from here, and then we are going to get this expression here. Now on simplifying this, we will get cosine x e to the power negative t plus sine x minus sine x times. Now if we consider this expression up to infinity and take negative sign as common, we'll get e to the power negative t. Therefore this negative sign is here. Now further, if we simplify this expression, we are going to get cosine x times e to the power negative t plus sine of x times 1 minus e to the power negative t. So this is the solution of the given problem in the t direction as we solve it. Now if we want to solve this problem in the x direction, what we need to do is we need to apply the Lx inverse operator on the both sides. So if we apply Lx inverse on both sides, then we are going to get this expression, and if we simplify this, this remains as it is. On the right hand side, we have ux comma t minus u of 0 comma t minus x ux of 0 comma t, and then Lx inverse sine x means that we need to integrate it twice from 0 to x. So this gives negative cosine x, so negative cosine x minus 1 when we apply the limits, and if we integrate this again, then we are going to get negative sine x plus x from 0 to x, and we will get negative sine x plus x. So we need to add this term here, that is negative sine x plus x. Now we need to retain this term on the right side and move all the terms on other side, so that will give us sine x minus x plus u of 0 comma t, that is given as e to the power negative t, then plus x ux of 0 comma t. So this is a function of t, we can write it as h of t, and plus Lx inverse applied on ut. So the first term of the series will be sine x minus x plus e to the power negative t plus x h of t. Now for u1, we first need to differentiate this with respect to x, because this is with respect to t, because this is ut. Therefore sine x will be 0, x will be 0. Here we will get negative e to the power negative t plus x h prime of t, that is the first derivative of t. And similarly for u2, we need to differentiate this. We differentiated this with respect to t, but Lx inverse is applied, so we need to integrate it also. We need to integrate it twice, so we get negative x squared over 2 factorial e to the power negative t plus x cubed over 3 factorial h prime of t. So this is u1. Now in the similar manner, if you want to find u2, we are going to do the same thing. First differentiate this function with respect to t because of this ut inside L(x) inverse operator. Therefore, the integral gives this x cube over 3 factorial h double prime of t. This is the differential with respect to t. Now, if we integrate it twice, we are going to get x to the power 4 over 4 factorial e to the power negative t plus x to the power 5 over 5 factorial h double prime of t. Now, similarly, we can find the other terms, that is u3, u4, u5, and so on. Now, if we need to combine all these terms, so we can just write in the series expansion, but we know that this h of t is unknown here, so we can use the initial condition. Therefore, ux comma 0 is cosine of x. We are using the initial condition here to find h of t. So this equals sine x minus x plus e to the power 0 plus x h of 0. Then we have u1, that is negative x squared over 2 factorial e to the power 0 plus x cube over 3 factorial h prime of 0, and so on. All right, now we can see that now this is e power 0, that is 1. This factor, this is 1. Then this is negative x squared over 2 factorial, and here we will have positive x to the power 4 over 4 factorial, and so on. Therefore, if you combine all these terms, this will give us as cosine of x. So all these terms which make cosine x will be cancelled with the cosine x at the left hand side. Now we are left with, if we move these terms to the left, we will get x minus sine x equals x h of 0 plus x cube over 3 factorial h prime of 0, and so on. Therefore, h of 0, if we compare with this, we will get h of 0 equals to 1. This is negative sine x, which means that if we expand this in the Taylor series, the Taylor series of sine x is x minus x cube over 3 factorial plus x to the power 5 over 5 factorial, and so on. Therefore, this is negative sine x. So negative sine x equals negative, positive, and this will become negative, and so on. So now, okay, so we have one more term here. So we cannot conclude that h of 0 is 1. Now, if we combine these terms, we'll get x minus x plus x cube over 3 factorial, and so on, equals x h of 0 plus x cube over 3 factorial h prime of 0, and so on. Now, if we compare the coefficients on the right hand side with the left hand side, this x cancels with this x. So x h of 0 equals 0, which means that h of 0 is 0. H prime of 0 equals 1, because the coefficient of x cube over 3 factorial is 1. Similarly, h double prime of 0 will be equals to negative 1, and so on. Therefore, now we can find h of t in the Taylor series expansion. We know that this equals h of 0 plus t times h prime of 0 plus t squared over 2 factorial times h double prime of 0, and so on. Therefore, h of t equals h of 0 is 0 plus t times h prime of 0, that is 1, so positive t. Then this is negative, and so on. Now, this can be a series of some known function if we add 1. So in order to add 1, we need to subtract 1 as well. Therefore, let us do this thing here. Now this, we can write it as h of t equals 1 minus 1 minus t plus t squared over 2 factorial and so on. So it gives us 1 minus e to the power negative t. So h of t is 1 minus e to the power negative t. Now we can plug in uh, here the values, right? So now let us erase this to solve it further. Now u equals u naught, so that is sine x minus x plus e to the power negative t plus x times h of t, that is 1 minus e to the power negative t. Then u1, so u1 is negative x squared over 2 factorial e to the power negative t plus x cube over 3 factorial times h prime of t. So h prime of t is e to the power negative t. And similarly, we have u2, that is x power 4 over 4 factorial e to the power negative t plus x to the power 5 over 5 factorial into h double prime of t. So h double prime of t will be again negative e to the power negative t and so on. Now we can just simplify this expression and we will get the desired result for this problem. So now we can see that this is sine x here, okay, and now this is negative x here. This one is negative x and this is positive x. So this negative x cancels with this positive x. So we left with sine x plus, if we take e to the power negative t as common in these expressions, so this we will get 1 minus x squared over 2 factorial. This one, then this one, positive x power 4 over 4 factorial and so on. And again, x times, then this one x times, so negative e to the power negative t. So this will give us negative e to the power negative t into x minus x cube over 3 factorial, this term here, and then plus x to the power 5 or 5 factorial and so on, this term. Now we have sine x plus e to the power negative t times this expression, that is for cosine of x, minus e to the power negative t times this expression, that is for sine of x. Now we get the result as plus sine of x into 1 minus e to the power negative t. So this is the result that we get by solving the problem in the x direction and the t direction as well. So the solution to the problem is given here. We can just verify the conditions and the equation given in the question. So this is how we can solve the problems associated with the heat equation using the Adomian decomposition method in any of the direction. So that's all for today's lesson. And in the next lesson, we'll consider some more problems on the topic partial differential equation, solving it by using the method of Adomian decomposition. Thanks for watching the lesson.